So let's walk through some of the fundamentals for our experiment this week on recrystallization and chemical extraction. So we're going to talk a little bit about what we learned last week in our mini experiment, and then we're going to go into what is recrystallization, what is an extraction, and how do they work and allow us to purify a compound. So what we saw last week was a quick experiment with some salicylic acid. And what we found is that there's two ways that we can change the solubility of salicylic acid. And in fact, for both of our experiments this week, both recrystallization and extraction, they're built upon the idea that if we can change the solubility of a compound selectively, we can use that to purify that compound. And what we found is that we could, in fact, heat salicylic acid up in water, and we would see that the solubility would increase dramatically. And as it cooled back down, that salicylic acid grew into those nice crystals along that wooden stir stick that we were able to observe. The other thing that we could do is actually change it through a chemical reaction. So if we reacted salicylic acid with a base, we could undergo an acid-base reaction, and our conjugate base of salicylic acid now has this negative charge and it's highly soluble in water. The general trend that we can see is that most organic molecules are not very water soluble. However, if they have a charge, if they have a formal charge, a positive or a negative charge, the solubility increases dramatically inside our solution. So if we added an acid to salicylic acid, nothing would happen because that's an acid and an acid, right? You need to actually be able to change the chemical structure in order to change that solubility. So this leads to a few of our solubility rules that we can use, right? The first dating all the way back to general chemistry, being that compounds dissolve in solvents that have similar intermolecular forces, right? This is a more complete way of saying like dissolves like. So if things have matching intermolecular forces, they are much more likely to be soluble or miscible if we are talking about liquids. Our second solubility rule is that compounds in general are more soluble in hot solvents. And our third solubility rule is that ionic compounds are more soluble in water than neutral organic molecules. So let's see how this goes, or how this works in action for recrystallization and extractions. So let's start with recrystallization. What we're going to be doing this week is purifying salicylic acid that has a trace caffeine impurity. And so the idea of a recrystallization is that if we have two of these things that are in this solid mixture, and we can heat them up in water and let it cool back down slowly, only one of them will hopefully recrystallize. So I've kind of broken this down on the bottom here where we can see this change, where we can start with our salicylic acid and our caffeine in this solid mixture, right? As we heat this up in boiling water, they both completely dissolve, and so we would say that these are both aqueous now in our flask. And as this cools back down, ideally the salicylic acid will recrystallize where the caffeine will stay inside the solution. This is based largely on solubility. So let's take a second and run through a quick practice problem on how we use solubilities to better predict and understand how much of something might stay dissolved in solution. So this comes from the problems that are in the PDF, right? This is at the very beginning. And so we're given this kind of general framework where we have a mixture of actually caffeine and salt in this case, right? Sodium chloride. And we're going to suppose that 20 grams of this mixture is what we have, and it's 75% caffeine and 25% sodium chloride. And so what we first need to figure out is, well, how much caffeine and sodium chloride is in our sample? And so we have a total of 15 grams of caffeine, because that's 75% of 20 grams, and we have 5 grams of sodium chloride. So we're given these solubilities at the top of our page here, and these are the amount in the grams of each compound that would dissolve in water, or in 100 milliliters of water. So we can just use this like a conversion factor back from general chemistry. So our first question is how much of the caffeine from this mixture stays in solution at 16 degrees Celsius. So for this, we'll need to use those solubility table or the solubility information up at the top. And we can see that we have 1.35 grams is the amount of caffeine that will dissolve in water at room temperature. So no matter what we do, that 1.35 grams will always be dissolved in water. Well, how much could we expect to crystallize? Well, that would be the difference here, right? So I had 15 grams of caffeine to begin with. and 1.35 grams of that stayed in the water solution. That means that maybe, right, I could isolate a total of 13.65 grams of caffeine if my recrystallization went well. Let's look at our sodium chloride, our table salt, and we would see that actually all of that dissolves because a total of 35 grams could be dissolved in 100 milliliters of water at 0 degrees Celsius. And so if we cool this down, right, no matter what, if we only had 5 grams to start with, it is all going to stay dissolved in the water, right? So we can use and start to think about how these solubilities impact what we can do with a recrystallization. In this case, if we were trying to separate caffeine and sodium chloride, we could purify this through a recrystallization because all of the sodium chloride would stay in the water. So the big ideas for recrystallization, and when you watch the experiment video, you'll see some of these in action, is that solubility increases as temperature increases. And using these solubility limits, you could design a purification by recrystallization, right? If one of your compounds will be entirely soluble at cooler temperatures while a different compound would crystallize, you could purify something by recrystallization. In general, you want to do recrystallizations very slowly so you can build that crystal lattice carefully. If it crashes out of solution too quickly, then you can trap a bunch of the impurities in there, and it defeats the purpose of our recrystallization. One of the things we're going to calculate is what's called a percent recovery, and there's practice for this in the PDF, and there's actually a guide at the end of the PDF that walks you through how to do some of these calculations. But the idea of percent recovery is it'll never be 100%, right? You'll never get all of the material out of your solution because some of it will always stay dissolved in your solvent, right? Even if it's a small amount. So in general, right, if you get 100% recovery, you might have done something wrong in your calculation and you want to revisit that because almost always, in fact, I will say always, you should get a number that's lower than 100% and if you have a good crystal. So let's talk about the second half of our experiment. We'll talk about some of the foundations, right, for what we're looking at with the chemical extraction. So extraction is where we take a compound out of a solution, right? A very common and familiar extraction you might be used to is actually brewing coffee or tea, right? Many people, when you talk about, what is a daily, instance of chemistry, people talk about, brewing coffee and making, the hot water and you can do a pour over or whatever it might be. But the idea is you start with a solid that contains all of these chemicals, all of these flavors, right? All the caffeine, all that good stuff in there. And when you pour hot water over it, it extracts or removes or pulls out all these things from the ground up coffee beans. And at the end, you have two separate compounds, right? You have the liquid coffee and you have the leftover coffee grounds. What we're going to be doing this week is actually an unfamiliar extraction, right? Where instead of looking at coffee, what we're going to be doing is doing a liquid-liquid extraction. So we have ethyl acetate and water, and the ethyl acetate is an organic solvent. And so we could think of this as being, lots of carbons and hydrogens, right? There's a few oxygens in there. But these two things are what we call immiscible, meaning they do not mix. So just like your salad dressing, right, that you have to shake up and you can see those layers separate, ethyl acetate and water will not mix together. So let's start with a thought experiment of what would happen. So let's say we start with this molecule biphenyl. And this molecule here is an organic molecule. Again, it's all carbons and hydrogens. If I were to add this to this flask at the bottom of the slide, and were to shake it up, where do you think the biphenyl would go? Right? Which solvent would be better for dissolving biphenyl? Well, if we think back to our like dissolves like argument from general chemistry, or the more complete version that compounds with similar intermolecular forces, right, are soluble, the biphenyl is an organic molecule. Ethyl acetate is an organic solvent. So more than likely, the biphenyl would stay dissolved in the ethyl acetate and would not dissolve in the water layer. So let's do another thought experiment. Let's expand this a little bit, right? So we would have our biphenyl inside that ethyl acetate layer. So let's imagine that we had two different compounds. Let's imagine we had some biphenyl and some sodium chloride, right? These are both actually kind of white crystalline solids, so they look very similar. If we put this mixture into the flask and shook it up, what do you think would happen? Well, the biphenyl is still just an organic molecule, right? So the biphenyl should stay dissolved in the ethyl acetate. However, we know that table salt is very soluble in water. And so if we could zoom in and look inside this flask, what we would see is that the ethyl acetate layer would contain the biphenyl, and the water layer would actually contain the sodium chloride. This is an example of a liquid-liquid extraction, where we have two different layers inside our flask, and by having differences in our solubility, we can actually separate a mixture of solid compounds. So what are we going to be looking at this week in our experiment? Well, this week we're going to be looking at the four compounds shown here on the slide. So I have some code names here that we're going to use to refer to these. We have benzoic acid, benzophenone, aminophenol, and biphenyl. Now, benzophenone and biphenyl are what we call rocks. That's why they have the code names R1 and R2. We call these rocks because no matter what we do, these will always be organic soluble, right? The other way you could think about this is that benzophenone and biphenyl will never be soluble in water. And when we're looking this week, what we're going to have is we're going to have some unknown mixtures, and these unknown mixtures contain either R1 or R2, right? They contain either benzophenone or biphenyl, and one of the other two options. So either benzoic acid or aminophenol. So there's only two compounds in our unknowns for this week, and they contain one of our rocks and either benzoic acid or aminophenol. And so what we want to do is think about how we can use chemical extractions, if at all, to actually separate these compounds. And this is what we're going to be exploring in our chemical extraction video. So take some time, watch both of the experiment videos, work on the PDFs, and yeah, we'll see how we can change solubility and use that to purify compounds and study them.